Very good morning to all of you. We will start with DSP lecture and in continuation with the topics which we have discussed earlier. We have started with the last unit, you all know, and just two topics are left to wind up with the syllabus. And your midterms will start soon. So for that, the syllabus is your it's
ये वो 2 दिन की कटौती बंद कराना है ना उसका सर ना 10-15 दिन पहले फिल कर दो
So we will start with finite effect of word length. In that we have started. This is the last unit of your syllabus. And I will share my screen, check it whether it's visible to you or not, and just revise the things which we have studied earlier. Screen is visible. Yes, students all have joined. I think maximum students joined. Am I audible to all? Am I audible? Okay, okay. So just you visualize the topics which we have studied earlier. So we have started with the topic finite effect of word length and why it is important, why we have to study this topic, because everything will be done on the hardware. And if we are designing some hardware, it will have some limitations. So to avoid overflow of the data and to how to save that data in the registers, what are the values of filter coefficients, we have to truncate that values because we get very large values of these coefficients. It continues, the students are joining till now. I gave 5 minutes more to join. So rounding off and is very important, truncation is very important to save the data in the registers. Okay, so to convert analog to digital, we need a few steps to convert. You all know, you have studied in communication also these steps. So to improve the performance of hardware devices and to store the filter coefficients efficiently, we will use this finite effect word length concept and we will apply quantization effects to the data. So we have discussed what do you mean by rounding and truncation error. We have discussed overall number systems, how we can save the data, and you should know the conversion of all the number systems: decimal, binary, hexadecimal, and all. Rounding and truncation error. Rounding and truncation errors. We have discussed what do you mean by round off of the data. We have seen some examples also earlier. We have taken sign, magnitude, and 2's complement form of the data, negative number representation, positive number representation, all these things we have discussed earlier. Now, I have taken one example that consider number x whose original length is L bits. Let this number be quantized. It could be truncated or rounded off. Okay, we all know truncation means to eliminate few digits. Rounding means rounding that number to some nearby number. Okay, to B bits. Original length was L bits. Original length was L bits and we applied quantization or rounding off near about to B bits as shown below. The quantized number is represented by Q of x. This is my quantized number. Both x and qx are shown below. Note that B is less than L. This condition we all know. That's why we are applying rounding off, because we have to reduce the original length of the data to store properly that data. Okay, so this is my x, the original number having length L. Okay, now I applied quantizing or rounding off of the data and I reduced that data to B bits. Okay, so we can say that some error will be introduced. That error is known as truncation error. Epsilon t is introduced in the input signal and thus the quantized signal is given by this number. Is it clear? So this is my truncation error, rounding off error. The range of values of the error due to truncation of the signal is analyzed here for both sign magnitude and 2's complement representation. Clear, student? Any doubt? See, this I am repeating everything because it's almost 2 weeks we have taken the classes. Okay, Diwali vacation over now and I hope all are safe and healthy, wealthy at your homes with your family. And I want to tell you about our FDP. We are conducting one faculty development program in Electronics and Communication Department on the topic Internet of Things and machine learning. I think many of the students have registered in this from your class. If views are remaining, please inform them to register, and you can circulate this message to your friends also, those who are in engineering colleges. You can circulate this message. Anyone can apply, industrial experts can apply, academians can apply, students can apply for this FDP. And it's very good FDP we are arranging. Many experts are there from IITs and ITs, and from industrial exposure also they have. And we are having hands-on session, lab sessions are also there. So please attend this FDP. It's very much beneficial for you people. So please inform others also. And may I know how many of you have registered from your class? Do you know about this workshop we are conducting from 1st of December? 2 hours morning session and 2 hours after lunch session. So how many of you have applied? Yes, students from your class applied. Aditi, okay. And others, are you aware of this workshop? Okay, very good. So you can apply it all, and you can forward it to RTU everywhere, wherever are your friends. You can send this message, this brochure, and the message. Okay, 25, 26 is the last date for registration. So please apply for it. And we have good participation this time. So we will continue with the lecture. Truncation error for sign magnitude representation. For sign magnitude representation, when the input number x is positive, truncation results in reducing the magnitude of the number. जब नंबर पॉजिटिव है तो मैग्नीट्यूड कम होगा. Thus the truncation error is negative and the range is given by this. This is the range 2 to the power b minus 2 to the power minus l, which is less than 0. If it is sign magnitude form and number is positive, error is less than 0. Okay, this you have to write in your copy. Topics you have written, I think this we have discussed earlier also. For error positive, therefore the truncation error is positive when the number is negative. Okay, this we can get from this example. A very beautiful example is there. Let the number be x is equal to minus 0.375. This is my number. Okay, this is in sign magnitude form and it is represented as 1011. In binary form you can convert it. Okay, decimal number conversion you can do in binary, and after truncation of one bit, what I will get, qx is equal to 101. Is it fine? Qx will be 101. This is equivalent to minus 0.25 in decimal, but minus 0.25 is greater than this. You can see. एंड आफ्टर ट्रंकेशन ऑफ वन बिट 101 हो जाता है तो वो एक नया नंबर बन जाता है. ठीक है ना, इट विल बिकम अ न्यू नंबर. सो दैट नंबर इज minus 2.25. So after truncation, what we are saying that number is larger as compared to the earlier number. ओके, सो नेगेटिव नंबर में क्या होगा, तुम्हारी रेंज जाएगी पॉजिटिव की तरफ. ओके, देयरफॉर द ट्रंकेशन एरर इज पॉजिटिव एंड इट्स रेंज इज गिवन बाय दिस. सो द ओवरऑल रेंज ऑफ ट्रंकेशन एरर फॉर साइन मैग्नीट्यूड रिप्रेजेंटेशन इज दिस. So this is my overall representation. Clear? Now truncation error for 2's complement representation. That's very simple. For 2's complement representation, when the input number is positive, truncation results in a smaller number, जैसे पहले भी था, as in the case of sign magnitude number. Hence, truncation error is negative and its range is same as given in equation 10.2. जो हमने पहले equation लिखी थी, वो same equation ही रहेगी, and that is given by this 10.5 number equation. Clear? Next, round off error for sign magnitude and 2's complement representation. I think you have prepared your copy, so you can write in that also. सो फॉर साइन मैग्नीट्यूड एंड टूज कॉम्प्लीमेंट राउंड ऑफ, अभी हमने ट्रंकेशन एरर की बात की थी, नाउ वी आर टॉकिंग अबाउट राउंड ऑफ एरर. ओके, next week you are having your exams, so if you have any doubt, we can have your class on Saturday, that is I think it's tomorrow only. तो बेटा तुमको कोई भी डाउट्स हो तो तुम पूछ सकते हो कल, ठीक है ना. एक बार पढ़ लो जिससे तुम्हें पता चल जाएगा. The round of error is symmetric about 0 and its range is C. The error due to rounding may be either positive or negative and the peak value is this. This is the peak value 2 क्यों आ रहा है? Because we are discussing the binary concept. Okay, इसीलिए इसका base 2 है. The round of error is in the range. So this you have to remember. Numerical can be asked. They can give you L and B. You can they will tell you to find out the round of error or truncation error. Okay. Now we all know what is the process of quantization. We are limiting its height. Quantizing. Sampling नहीं कर रहे हम, quantizing कर रहे हैं. That means we are limiting its height. On the y-axis, it will be limited. Okay. So these three graphs shows all the effects of quantization, okay, and its range. So first is rounding off. Rounding करने से क्या होता है? The number is shifted equally to the positive and negative side. Plus x-axis and minus x-axis. It is in the center. So the limit is 2 to the power minus b by 2 to the power minus b by 2. Rounding off करने से, ठीक है. Truncation in 2's complement, the number starts only from your positive x-axis. This you can see this is symmetric about both and this is unsymmetric. If x is starting from 0, so it will move, q of x will be 0 only and it will move towards positive x-axis. यहाँ पे equal नहीं है, उसके बाद वो सीधा नीचे जाएगा, तुम्हारा quantization error negative. Okay, sign magnitude form में again equal but the range has changed to 2 to the power minus b to 2 to the power minus b plus b, sorry. So these graphs are very important. You can draw this in your copy. Finish drawing. So in continuation with this, so these are the formulas, approximate values. You can write this also. Infinite precision is assumed, that is the length of the unquantized number is assumed to be infinity, and as a result equations written above can be modified and the range of values of error for different cases are as follows. Infinite precision is assumed, okay, for unquantized number is assumed to be infinity. So we are getting this modified values as equation number 10.7, 8 and 9. You can compare both the equations. So truncation error for sign magnitude representation is 2 to the power minus b to the power minus b. For 2's complement minus 2 to the power minus b till 0. For round off it is 2 to the power minus b by 2 to 2 to the power minus b by 2. Okay. Shows the quantization error in truncation and rounding of numbers. In computation involves, now draw this graph. This is showing you the probabilistic characteristics of quantization error. In power density equation we are writing. So the graph is like your unit sample. Finished? Hello? Yes, students, voice is clear now? Yes, due to internet problem might be there. Okay, the quantizing unit is modeled as one that introduces an additive noise to the unquantized value of the number x. Q of x जो हमने define किया है quantized number. Power spectrum is shown here with the error in the graphs. So Q of x, the quantized number will be x plus this error, okay? Where epsilon is equal to epsilon r for rounding and epsilon for epsilon t for truncation. Clear? Now quantization effects in analog to digital signal conversion. Just in very short, we will discuss this topic as we will convert the signal from analog to digital. Quantization effects you can see very easily and some error will be introduced in that. So what is the process of analog to digital conversion? It involves sampling the continuous time signal at a rate much greater than the Nyquist rate. We all know what is Nyquist rate. Yes, students, what is Nyquist rate? Sampling theorem. कौन बताएगा? Who will reply? And second step is the quantizing the amplitude of the sample, very good, of the sample signal into a set of discrete amplitude levels. The input-output characteristics of a uniform quantizer is as shown in figure. This quantizer rounds the sampled signal to the nearest quantized output level. Okay, we are quantizing, this is my signal, we are quantizing it. We have sampled on x-axis and y-axis, we have leveled all these things and we have to follow the Nyquist criteria, frequency less than sampling frequency. So this width should be 2 to the power minus b, because b is your quantized number reduction level. Okay, so we have quantized this number. This quantizer rounds the sample. अब कोई वैल्यू यहाँ पे है, इस पॉइंट पे है, उसको भी हम कहाँ मार्क करेंगे? यहाँ. We are continuously increasing the values in step to step size. This quantizer rounds a sample signal to the nearest quantized output level. The difference between the quantized signal amplitude xq of n, this, and the actual signal amplitude x of n is called the quantization error. Got the point? Whatever, wherever is a signal lying, but we are quantizing it, so somewhere it's low, somewhere it's high, the quantized value, so that the difference between the quantized signal amplitude and the actual signal amplitude is called the quantization error. And this is defined by E of n, and that is given by E of n is equal to xq of n minus x of n. This is the error. So draw this diagram and write down this. Heading क्या थी इसकी? Quantization effects in analog to digital conversion of signals. And this diagram and this equation are important. Finished, students? So this finishes your topic of this. You can write the signal, this limit rounding is involved in the process of quantization. The range values for the quantization error is this. You have written earlier also. This is E of n, okay? Error generated. Now we will just write down the signal to noise ratio SNR. You have all heard what is signal to noise ratio. The SNR can be evaluated to quantify the effect of the additive noise E of n. The SNR is given by this equation. We all know the signal power upon the power of the quantized noise, output power upon the input power. And here we are finding after quantization. So it is the signal power Px of n upon Pe of n, which is the power of the quantized noise. And in the process of quantization, the sample value is rounded off to the nearest quantization level. The probability density function, that is PDF, in RVSV, random variable stochastic processes or mathematics, you study this word PDF for the quantization round of error in A to D conversion is shown in figure 10.4. You can see this graph is very important. It is showing you the power concept, probability density function for the quantization round of error. Finished? Okay. So now just write down the SNR equation in the form of variance. It is mentioned and it is simplified actually. So do this derivation. The power of the quantization noise, which is nothing but the variance, sigma square, is given by, write down this equation, PE of n power is equal to variance. Variance is sigma square. Finish this. PE of n is coming out to be 2 to the power minus 2b upon 12. So now SNR equation is given by 10 log Px of n upon Pe of n. And this can be written as Pe of n को मैंने substitute कर दिया है. Got the equation? Any doubt? So this is the important equation. They can ask you signal to noise ratio. What is the quantization error due to analog to digital conversion? So you can tell there. And very important, this equation, SNR 10 log Px of n plus 10.8 plus 6b, which indicates that each bit used in A to D conversion or in the quantizer increases the signal to noise power ratio by 6 dB. Alternatively, equation can be written as this equation. PE of n जो है 10 log PE of n यहाँ find करना है हमें, which is given by this, and it could be written minus 10 log 12. Finished writing this equation? And alternatively, this equation is known as a dynamic range of quantizer. dr, that is dynamic range. वो जो हमें मिल रहा है PE of n से equation 10 log, I got this minus 6b minus 10.8, which is known as the dynamic range minus 10 log PE of n, which is given by this 6b plus 10.8. So this finishes one of the topic of finite effect word length. Now I will just discuss in brief multi-rate DSP. What do you mean by multi-rate signal, students? Means you have seen in digital audio the different sampling rates are used in broadcasting. You have seen FM. So many ranges are there: 92.4, 92.6, 98 point, 100. In this way, we are having different frequency ranges. Okay, but the processor is one only. We don't have different processor to get different inputs of frequencies. We are having a single processor. That single processor is working on multi-rate on different frequency ranges. Clear, students? So their multi-rate DSP is very important in broadcasting of different signals. So different sampling rates we can get. We are having a single input in between the processor. Like I can give you example. If my DSP is designed to work on 98 megahertz frequency, okay, now I want to change the frequency to 98.5 megahertz. Then what I will do, I will use a different processor. Likewise, in between I need 100 megahertz frequency to process. Then again I have to use a third signal processor. Okay, so it is not feasible to have n number of different processors for different frequency range to execute the same application. What I will do here, I will use the concept of upsampling and downsampling to get multi-rate DSP. In the same processor, I can get different frequencies. So different sampling rates can be obtained by using an upsampler and downsampler. Okay, the basic operations in multi-rate processing to achieve this are known as decimation and interpolation. These are two words used for upsampling and downsampling in multi-rate DSP, and it is of very interesting topic and of very much use in, as I can say, so much of research work is going on multi-rate DSP. It is a topic in masters. They have this topics in very much detail. You are having just one topic, multi-rate DSP, I think, in your syllabus. So for that, you should know interpolation and decimation, upsampling and downsampling. Okay, decimation, by the word you can say, it is used for reducing the sampling rate. Clear? Decimation is for reducing the sampling rate and interpolation is for increasing the sampling rate. In digital transmission systems, like initially we used to do fax, facsimile, teletype, low beat rate speech, where data has to be handled in different rates. Like I'm speaking now, continuously my frequency is changing, up, down, it's going on. Okay, so there I need different range of frequencies. So there in digital transmission, many examples are there where we have to handle the data at different rates. There I will use multi-rate signal processing. Multi-rate signal processing finds its application in many areas. Voice privacy, A to D converters, D to A converters, signal compression and telecommunication, in fax, communication systems, antenna systems, radar systems. I need this because all my signals are coming from different sources and they are having different frequencies, and my processor should be that much active to process all those frequencies. Okay, so there are so many advantages of multi-rate signal processing. Advantages are computational requirements are less, storage for filter is very less, finite arithmetic effects are less, filter order required in multi-rate applications are low, and sensitivity to filter coefficient lengths are very less. So there are so many advantages. So in next class we will discuss with sampling rate conversion how we can convert it and how I can design a decimator and interpolator. So anything you want to ask, student? We'll wind up the class over here. So if any doubt, you can ask. Interpolation and decimation पढ़ना है बच्चों, ध्यान रखना. This is a very good topic and very interesting. Numericals can also be asked on this topic. So we will wind up this class. Anything you want to ask? I'm waiting. And please inform others also about the syllabus, about examination, because many students are so just one more topic is left in your syllabus, that is spectral estimation of parametric and non-parametric signals. In that totally it's mathematical, power distribution, power density function, PDFs we have to study over there. So next class we will discuss. So goodbye students.